All right, coming into the examples that we worked last class, I mean, clearly at this point, we definitely know how to integrate sine and we know how to integrate cosine. And if we have something that is a chain rule where your inside function is a cosine or a sine, then we will know how to handle it. So we did several examples last video on where we had an inside function that was cosine of 2x, and then we were looking for the derivative of our inside function, negative 2 sine of 2x dx, and then we worked through several examples where we saw that. Now, what we want to do is kind of show you a little bit more. We're going to work a little bit more with trig integration to kind of make sure that we really understand how the trig integration works and some of the different things that we might see using this U substitution or pattern recognition technique. We're first going to take a look at something like this. And one of the things that you want to recognize is that you can actually work this problem two different ways. One is to recognize that the derivative of tangent is secant squared. And so when you're looking at like this idea of identifying an inside function whose derivative is on the outside, that a lot of times when you actually have a product like this, you're going to make a decision that one of the items is going to be your, shall we say, u, and then the other one needs to be the derivative of that. So in this problem, the first way, method 1, I'm going to let my u equal tangent of x, because then my du, my differential in u, derivative of tangent is secant squared x dx. And so I can tell that I can essentially think of this as u to the first, and then the stuff that's on the outside is going to be the derivative of the u that we're looking at. So I'm going to do secant squared x, then I'm going to have the tangent of x, and I like to reinforce where I have my box, I guess you would say, when I'm doing this problem, that my box with my u in it is right here. So I am going to integrate this. I'm going to ignore this portion and that portion because these are the du's. This is what's getting packed back into the box from chain rule. So I have u to the first. The antiderivative of u to the first is u to the second times 1/2 plus c. Okay, so that's going to give me 1/2 tangent squared x plus c. So that's method 1 for calculating this integration. See, but the idea here, and this is why integration can typically sometimes be difficult, is there's always more than one way to work a problem, and that it all depends on kind of how you want to approach it. So we're going to do this a different way. Instead of making the u the tangent of x, I'm actually going to first rewrite it and make it secant of x, tangent of x. Because secant tangent is a known derivative, and it's the derivative of secant, I'm going to choose in this technique to make my inside function, okay, the secant x. So I'm going to let my u equal secant of x, then my du is going to be the secant x tangent of x dx. So I kind of keep that in mind. And so when I go to rewrite this, I'm going to rewrite it as secant of x to the first, again, just emphasizing where the box is that I'm packing things back into. So when we look at this, this is my u to the first, that's my box. I am going to integrate, and when I integrate, the antiderivative of u to the first is going to be u squared with a 1/2, and then of course this goes away because we pack it back in the box, plus c. So this is going to give me 1/2 secant squared x plus c. Now at this point you might be like, wait a minute, how are these things the same? That's where this plus c comes in. I'm just going to come over here and kind of show you using this one. remember that with your Pythagorean identities, maybe we'll write it up here, Pythagorean identities. There's cosine squared x plus sine squared x is equal to 1. And then if I divide everything by cosine, I get 1 plus tangent squared x equals secant squared x, or tangent squared x equals secant squared x minus 1. So this tangent squared right here, I'm going to take that out and replace it using the Pythagorean identity. This is secant squared x minus 1 plus c. This would equal 1/2 secant squared x minus 1/2 plus c. And really what you're going to recognize is that these two things are the same. That's what this constant of integration is going to adjust for. This minus 1/2 plus c and this c over here can be treated as the same thing. You basically have 1/2 secant squared of x plus a number. And in one problem, the number will come out to be one thing, whereas this c over here will be a little different. You can kind of, if you want to be more technical about it, we would say maybe we'll call this one c2, because it was the constant over on this side, and we'll say this is going to be where c2 equals negative 1/2 plus c. And so you can kind of see that the different processes give you what may look like different answers, but they really are equivalently the same answer, just in different forms based on your trig identities. All right, let's take a look at the next few examples. Okay, so we're looking through here and we're like, oh, this has got some real complication going on. And what I look at is I go, oh, maybe let's make this the inside function. And I'm going to be honest with you, there are times when you do these, if you choose an inside function and it doesn't work, you just back up and try a different technique. So a lot of times with integration, you can't be afraid to fail or to try something that doesn't work. You try it and then you either luck out or you keep going, or you back up and choose another choice for an inside function. So I'm going to choose this to be my u, 5 to the x cubed plus 7. I'm going to take its derivative. The derivative of 5 to the x cubed plus 7 is 5 to the x cubed plus 7 times natural log of 5 times, now I need the derivative of the inside, 3x. Okay, so now I start looking, and then of course dx. So then I start looking here and I see that I have a 4 here, and there's no 4 here, so that must be a writer. So I'm going to pull that out. So I'm going to do 4, and I like to leave some space in case I have to add some things in. Oh, and that should be x squared, because the derivative of x cubed is 3x squared. All right, and then we look at this, and I see that I have x squared, and here's an x squared, so that's part of the derivative. I have a 5 to the x cubed plus 7, a 5 to the x cubed plus 7. So that's part of the derivative. And then I see that I'm missing some things. So I'm going to need some corrections in here. I'm missing the 3 and the ln of 5. So I'm going to put in the 3 and do a 1/3. I'm going to put in the natural log of 5. And then I'm going to start cheating over here. I'll just divide by natural log of 5. Yes, I'm doing the reciprocal 1/, but I can just divide. So that gets my corrections in there. So now we're ready, and then what we have left over here is the secant squared of the inside function of my u. X cubed plus 7, and then my dx. So here's my box that I'm looking at, and my box is secant squared. And secant squared is a known derivative. I know secant squared is the derivative of tangent. So secant squared u, its antiderivative is tangent of u. And remember, I'm ignoring all of this stuff here because that gets packed back into the box. And I bring along my constants, my writer and my corrections. So I end up with 4/3 natural log of 5, tangent 5x cubed plus 7, and then I add my plus c on over here. So my choice of the inside function worked out. Now, just kind of as a heads up of, I've been doing this a little bit longer than you guys, obviously. Why, when I looked at this, why did I not decide to make this secant of 5x cubed plus 7 and then square it and call this the inside function? The reason being is because if that had been my inside function, its derivative, the derivative of secant, is secant tangent. And there's no secant tangent out here to match with it. So that's why I knew that that was not going to be kind of a good choice on this problem. So you kind of, the more you work with these, the better or easier it'll be to see your U substitution so that you can choose the correct U substitution to do the problem. All right, so let's look over here. And again, very complicated looking, but we kind of skip over all this stuff and then we recognize that I've got this cosine of 5x cubed right here. And I think I'm going to make that my inside function because the derivative of cosine is going to have a sine in it, and that will take care of this. And because this is 5x cubed, its derivative would have an x squared. So I kind of make a decision about what I want u to be. So cosine of 5x cubed. I find its derivative, just double check here. Derivative of cosine is negative sine. Then I use my chain rule times my 15x squared. Then we start rewriting this. I look at this 22 and I say, not in my derivative, so that's a writer. Pull it out. Leave yourself some space. The x squared is good. The sine of 5x cubed, that's part of it, sine of 5x cubed. And then I say, well, I'm missing, I always forget to put the dx on the end, I'm missing the negative and the 15. So I'm going to have to put in a correction. I put in the negative 15, I take out the negative 15, and then I know that what we have left, my e to the cosine of 5x cubed dx, that there's the box that is identifying what I'm actually integrating. So I'm integrating e to the u. The antiderivative of e to the u, again, ignore all of this complicated stuff. It gets packed back into the box. So I'd have negative 22 over 15. And then I would end up with the antiderivative of e to the u is e to the u. And plus c. And you can take the derivative of this and check and see if we end up back to the integrand that we had. But that is something, just a little practice that we're going to work on this. And just remember the steps that I'm going through. I identify an inside function. I find the derivative of the inside function. I pull any constants that are writers that have nothing to do with my derivative out. I see if there are any constants that I'm missing from the derivative. I put those back in with the correction. And then I identify the box, what I'm actually integrating. The rest of the stuff can be ignored. It gets packed back up in chain rule, stuffed back into the box. So I only have to worry about integrating e to the u. All right, now we already know the following trig antiderivatives. The antiderivative of sine is going to be negative cosine of x plus c. The antiderivative of cosine is going to be sine of x plus c. Our antiderivative of secant squared, that's the derivative of tangent, so this would be tangent of x plus c. The antiderivative of cosecant squared is going to be negative cotangent of x plus c. Our antiderivative of secant tangent is going to be secant x plus c. And our antiderivative of cosecant cotangent is going to be negative cosecant x plus c. So those are ones that are known derivatives, so that you should be able to not only take the derivative and work forward, you should be able to take the integral and work backwards. Okay? And now we're going to expand our knowledge, because notice that we have a sine and a cosine inside of here. We don't have a tangent though. Oh, so maybe we should think about how do we integrate a tangent. I also don't have a cotangent as one of my choices. So I have these four basic trig functions that I would like to be able to work backwards to find an antiderivative for. Now I am going to tell you that I'm going to show you how we're using this u substitution to work our way back. We're going to be a little clever about it, but essentially at the end you're just going to need to memorize these as rules as well. So if I was going to integrate tangent of x, what I'm going to do, my clever trick, is to rewrite this as sine of x over cosine of x dx. And when I do that, what I'm going to decide to do is I am going to let u equal the denominator. Okay, we'll talk about why in a second. We'll kind of come back to this. I'm actually previewing this right here. I'm previewing what is in section, for you guys, section 5.7. I won't tell you what it is yet because we're going to work our way toward it. That if I want to integrate this, that I'm going to let u equal the denominator, cosine of x. That's going to be my quote-unquote inside function. Alright, so I calculate its derivative, du. The derivative of cosine is negative sine of x dx. And so now I'm going to notice that I'm missing, for my constant correction, I need a negative, and so I'll put a negative in up here. And so when I go to integrate this, what I'm going to be really integrating, and I'm going to go ahead and do the u substitution this time, is negative antiderivative of 1 over u du. 1 over u du. So by my choice of choosing to make the inside function the denominator of the fraction, hopefully at this point you might be going, wait a minute, 1 over u, that's a known derivative. That is the derivative of the log function. Okay, so working backwards, bring your negative down. The antiderivative of 1 over u du is the natural log of absolute value, because we have a domain problem here, plus c. So that gets me to there, and then I am going to do negative natural log. Remember, you got to go back to the variable you had, cosine of x plus c. So this process right here is where we're now going to do u substitutions with integrals that end up being logarithmic. So section 5.7 is your log rule for integration. Alright, so what we're typically looking for, okay, when we're integrating, if I have the antiderivative of 1 over x dx, that's your natural log absolute value of x plus c, and that when we are doing our quote-unquote u substitution, we're trying to end up with something where we have 1 over u du, so that I can do ln absolute value of u plus c. Okay, so in all of these new trig ones that we're learning, this is actually coming in your section 5.7, which is, these are going to be some new rules. You're going to add them to your list of things to memorize, but if if you forget them, you can create them again by simply using this trick. Alright, let's look at the cotangent one. Very similar. I'm going to first rewrite it as cosine of x over sine of x dx. And so I'm going to let you, and the trick to these log rule for integration is you always let your quote-unquote inside function be the denominator in this. So you recognize that if I let u equal the denominator, sine of x, then you hope that your du is the numerator. So du, derivative of sine, is cosine of x dx. And so we're really basically integrating here 1 over u du, because cosine x dx is your du. And so the antiderivative of 1 over u du is going to be natural log absolute value of u plus c, which is going to be natural log absolute value of sine of x plus c. So that gives us our antiderivatives for tangent and cotangent. And again, just memorize them. But this idea of using the log rule is a technique that you're going to be using in section 5.7. All right, now let's take a look at this next one. And we're going to employ a little bit different trick on this one. On the secant of x, what we're going to do is I'm going to multiply by a convenient form of 1. That's going to be my trick. So I'm going to take the secant of x that I had, and I'm going to multiply it by secant x plus tangent x. Okay, and so we have our dx in here. Now when I do that, notice that I'm going to end up with, on the top, secant squared x, which is a known derivative of something, plus secant x tangent x, which is a known derivative of something, all over secant x plus tangent x. And remember that the trick that we're talking about here when we want to use this log rule for integration is we're always going to make our u substitution our inside function the denominator. And we are going to hope that when I do that u substitution, that the derivative of the u ends up being the numerator. And you will see very nicely the derivative of secant is secant tangent, and the derivative of tangent is secant squared. And of course this is all times dx. And if you compare this to my numerator, we go, hey, yay! That means that the bottom is my u, and the top plus the dx gave me the du. So I have turned this into the log rule integration. And so we can come down here and take our antiderivative, the antiderivative of 1 over u du, natural log, absolute value of u, plus c, natural log, absolute value, put our u back in, secant x plus tangent x plus c. So here we are. The only way, which kind of starts to be interesting, the only way to actually integrate these other trig functions was by being clever and creating a situation where I could use the log rule for integration. All right, now you have one more over here to do. Part D, I'm going to leave that one for you to do on your own and then check your answer. It's going to be in your textbook in section 5.7. So if you will complete that one on your own, that'll save us a little bit of time in this set of notes. Okay, and then just to kind of play around with this, I think also what I'm going to do here, because I think practice is really going to be how you're going to learn these. So before we come in for the next class, probably what I would like you to do is to go ahead and maybe try to integrate 11. So let's have you do example 11. Let's have you try example 12 as well, to kind of set yourself up, let you have a little bit of practice in working toward how would I do these integrations. And then we'll discuss them in class next time. All right, now I would like you to we'll stop here because now this section, starting on example 14, okay, in example 14, we are now going to start looking at, hopefully you'll recognize that those are derivatives of known inverse trig. So this is actually going to be the start of section 5.8, which is integral rules for inverse trig. And I'm going to stop the video here and pick that up in a separate video.